Remember waiting minutes for your computer to boot up, that sluggish grinding sound, a constant reminder of slow data access? That mechanical bottleneck defined computing for decades, limiting not just speed, but also the very form factors of our devices. But then, a quiet transformation began, fundamentally redefining what a computer could be and how we interact with information. We're going to unpack the HDD bottleneck that held us back, explore the fundamental technology behind solid-state drives, and reveal how they sparked a revolution across everything from your laptop to the cloud itself. For nearly half a century, the hard disk drive, or HDD, was the undisputed king of data storage. It's an ingenious piece of engineering, spinning platters of magnetic material, read by tiny heads flying mere nanometers above the surface. But its very genius was also its Achilles' heel. Imagine trying to find a specific paragraph in a 1,000-page book by having a robot arm frantically searching for pages, flipping back and forth. That's essentially what an HDD does. Every time you open a program, load a file, or boot your operating system, those read/write heads have to physically move across the platters. This seek time was the ultimate performance constraint. This mechanical dance meant HDDs were slow, susceptible to physical shock, and generated heat and noise. It meant laptops had to be thicker to accommodate the spinning disks, and every application launched felt like an eternity. The more complex software became, the more data it needed to access, and the slower the HDD made everything feel. Even the fastest processors could only crunch data as quickly as the storage drive could deliver it, creating a persistent bottleneck that starved our CPUs of the information they needed. Then came the breakthrough: solid-state drives, or SSDs. Unlike their mechanical predecessors, SSDs have no moving parts. Instead, they store data on interconnected flash memory chips, similar to the USB drives or memory cards you use every day. This simple change eliminated the mechanical bottleneck entirely. Data isn't sought on a spinning platter. It's accessed electronically at near instantaneous speeds from a grid of memory cells. This fundamental shift wasn't just an upgrade. It was a re-architecture of how computing systems handle data. SSDs leverage NAND flash memory. Think of NAND flash as a vast, organized grid of tiny electrical gates that can store a charge representing a 0 or a 1. This non-volatile memory retains data even without power, making it perfect for permanent storage. Early SSDs used single-level cell, or SLC, NAND, which stored 1 bit per cell, offering extreme durability and speed, but at a high cost. As technology advanced, multi-level cell, triple-level cell, and now quad-level cell, NAND emerged, storing 2, 3, and 4 bits per cell respectively. This increased storage density, making SSDs more affordable, though often at the trade-off of slightly reduced endurance and speed for individual cells. The controller is the brain of the SSD. It's a tiny processor that manages data flow, performs error correction, and handles crucial tasks like wear leveling. Because NAND flash cells can only endure a finite number of write cycles before degrading, the controller ensures data is spread evenly across all cells. This wear leveling extends the life of the drive significantly. It also manages garbage collection, optimizing space by consolidating data and erasing invalid blocks, preventing performance degradation over time. The sophistication of this controller is often what separates a good SSD from a great one. The immediate impact of SSDs on personal computing was transformative. Boot times, once measured in minutes, shrank to mere seconds. Applications that used to crawl to load now snapped open instantly. Games loaded faster, file transfers became blazing quick, and the overall responsiveness of a computer felt dramatically improved. Users no longer tolerated the sluggishness they once considered normal. This wasn't just a marginal improvement, it was a fundamental shift in user experience. Beyond raw speed, SSDs brought other critical advantages. Their lack of moving parts made them inherently more durable, surviving drops and bumps that would instantly destroy an HDD. They consumed less power, extending laptop battery life and reducing heat generation. And critically, they were completely silent. The hum and whir of a traditional hard drive became a relic of the past, contributing to quieter, more pleasant computing environments. This combination of speed, durability, power efficiency, and silence made SSDs indispensable. The true revolution, however, wasn't just faster existing devices, it was the enabling of entirely new ones and new computing paradigms. The ultra-thin laptop, like Apple's MacBook Air, became possible because SSDs didn't require the physical space or shock protection of an HDD. Smartphones and tablets, with their instant-on capability and robust durability, rely entirely on flash memory, a direct descendant of SSD technology. Without the compact, durable nature of SSDs, these ubiquitous mobile devices simply couldn't exist as we know them. The impact also rippled into enterprise and data centers. Server farms, once filled with racks of power-hungry, heat-generating HDDs, began to integrate SSDs. While more expensive per gigabyte initially, the total cost of ownership often proved lower due to significant reductions in power consumption, cooling requirements, and physical footprint. SSDs allow data centers to process vast amounts of information with unprecedented speed, fueling the growth of cloud computing, AI, and big data analytics. The instant access demanded by modern web services and real-time processing would be impossible with traditional spinning disks. The evolution of SSDs didn't stop there. Early SSDs communicated via the SATA interface, originally designed for HDDs. But as SSDs became faster, SATA became a new bottleneck. This led to the development of NVMe, or Non-Volatile Memory Express. NVMe is a communication protocol built from the ground up specifically for flash memory, connecting directly to the CPU via the PCIe bus. This dramatically reduced latency and increased throughput, unlocking the full potential of high-speed flash storage. NVMe drives are now standard in high-performance computing, offering speeds several times faster than even the fastest SATA SSDs. Despite their advantages, SSDs did face challenges. Initial pricing was a major barrier, making them a premium component. Concerns about write endurance, while largely mitigated by wear leveling algorithms, also gave some users pause. However, continuous advancements in NAND technology and manufacturing processes have driven prices down dramatically, making SSDs accessible to almost everyone. Modern QLC NAND drives offer capacities comparable to HDDs at increasingly competitive prices, further accelerating the transition. One common misconception is that SSDs are fragile or that filling them up completely will shorten their lifespan. While it's true that flash cells have a finite number of write cycles, modern SSDs are engineered for many years of typical use. The wear leveling algorithms are so effective that most users will upgrade their computer long before their SSD reaches its write limit. As for filling them, leaving a small percentage of free space, perhaps 10 to 15%, is generally recommended for optimal performance, allowing the controller sufficient room for background maintenance tasks like garbage collection. What's next for solid-state storage? Researchers are constantly exploring new memory technologies like MRAM or RRAM, which promise even faster speeds and greater endurance. Hybrid solutions, combining traditional DRAM with NAND flash, are also emerging to bridge the gap between volatile and non-volatile memory. We're seeing greater integration directly onto CPU packages and new form factors that push the boundaries of miniaturization even further. The journey from spinning platters to instantaneous flash storage has reshaped our digital world, and the innovation continues. So, the next time your computer boots in an instant, or you marvel at the thinness of a laptop, remember the quiet revolution brought about by solid-state drives. They didn't just make our computers faster, they fundamentally changed what computing is and what we expect from it, laying the groundwork for the always-on, instant access world we inhabit today. Just remember, everything here is for education, not personal technology buying advice. Your specific needs are your own, so do your own research before you make any decisions. If you found this explanation helpful, consider subscribing for more deep dives into the tech that defines our world. Stay curious. This is AI Unpacked.